Good morning, everybody. Welcome to the last round of this year's Young Taiwan Business Students Forum. Since the year 2009, this is an annual event organized by the Physics Department of the National Taiwan Normal University in cooperation with the Xu Youxiang Memorial Foundation. I'm here speaking as the chairperson of the jury who will work together to evaluate the participants' performance in this last round. For the last 5 days, we have conducted 5 preliminary rounds. There were 20 teams representing 10 high schools from Taiwan took part in the selected rounds. I'd like to take this opportunity to thank all the students who participate in the select round to show their support of the cause of this forum. According to the regulation of the tournament, however, only 3 teams are eligible for today's final round. These were teams who achieved the highest total sum of points during the preliminary round. They are seated in front of you. I'd like to congratulate these 3 teams for their outstanding performance in the tournament so far. Now, to begin the first stage of the final round, I'd like to ask the captain of each team to introduce your team. We start first with the reporter team.
Good morning, everyone. We're Team Excel from Concordia Middle High School from Jiayi. And I'm Captain Peter, Alan, Mandy, Jason, and Belle. Thank you. Thank you. Good morning, everyone. We are both from KSHS, and this is Alan. This is Chen Yao. This is Carter. And this is Timus. And I'm Johnny. Thank you.
And next, the review team.
And good morning, everyone. I'm the team captain from Fire Drill Wolves, and we are from Kaohsiung Senior High School. And my name is Yisong Mu. And this is Wang Yaohui. This is Chen Mo Jun. This is Xie Dongjun. And this is Guo Shanyu. And thank you.
Now I'd like to introduce the for the recorder to prepare. Okay. Now I'd like to ask each team to send, to write down the name of your representative. And before the team, please also write down the problem number, okay?
Good morning everyone, we're Team Excel, and today we would like to talk about hearing light. And first is our presentation outline. We have problem, equipment, observation, experiments, and finally discussion and summary. The problem has been done coat one half of the inside of a jar with a layer of soot, then drill a hole on its cover. When the light from a light bulb connected to AC hits its black wall, a distinct sound can be heard. Explain and investigate this phenomenon. Okay, first we have our equipment. We have incandescent bulb, PVC tube, and use aluminum for your rapid insight and combine it like this. And here's a picture of it. And we have high sensitivity microphone, a glass jar, two kinds of software to help us record the sound from the microphone that analyze the spectrum of the sound. And first is our observation. We prepared a video clip.
As you can hear from the video clip, a small humming sound and it's also a low frequency sound appears when we turn the light, and it also disappears when we turn the light off. So that's the sound we are talking about today. And here I want to introduce our standard process of our experiment. First, before our experiment, we adjust all the equipment. And later, we record the sound for 3 seconds every time, and then analyze the spectrum of the sound. Okay, here's our experiment. First, our purpose is we want to determine the frequency of the small humming sound. And the following graph is our apparatus. We have a jar which contains carbon powder, since we know most of the jar contains most carbon. So we use carbon powder instead of soot. Then we use incandescent light bulb connected to the AC power coming from our power source. Then use microphone connected to computer. And here's the picture. Okay, the left-hand side is the background sound. The graph is a spectrogram. The x-axis is the frequency of the sound, and the y-axis is the intensity of the sound in the certain frequency. And as you can see from the background sound, it was very smooth and nothing special. But as we turn on the light and illuminate the jar, a very significant peak appears in 120 Hz. It became the highest point of our spectrogram. So we can know that it's the sound we heard was just 120 Hz. And we're curious about, is there any kind of relationship between the jar and its cover or the hole on it affect our frequency of the sound. So we did our further investigation. We just removed the jar and have the carbon powder on a metal plate. Then use the same method to do the experiment. And it's very clear that a peak also appears in the frequency of 120 Hz. So we can know that the sound frequency was 120 Hz. And the origin of the sound was the soot, which is we use carbon powder. And the jars was just acting like a resonant chamber, somehow amplify the sound, and it will not affect the frequency. And we are curious about, is there any kind of relationship between the AC frequency and our sound frequency? Since twice of the AC frequency equals the sound we heard perfectly, so we did our next experiment. We want to check the hypothesis that it's twice the AC frequency equals to our sound frequency. So this time this is the apparatus we use. It's similar to the last experiment, but this time we use an inverter to provide different frequency of the AC power to supply the light bulb. And here's the result graph. The left-hand side is background sound, and the right-hand side is the one we record after we turn the light. And the background sound is quite similar since they're very smooth. And a peak appears when in 300 Hz when we use 150 Hz of AC power. And 200 Hz of AC power, peak appears in 400 Hz. How about 250, a peak in 500 Hz. So from the experiment, we can know that the humming sound will be affected by the AC frequency, and twice the AC frequency just equals to our sound frequency. And our third experiment is that we want to find out the relationship between the light intensity and the sound intensity. Since when we turn off the light, the sound disappears. It also means that when the light is turned off, the intensity of the sound just decreases very soon. So here's our apparatus. The way we change our light intensity is to increase the distance between the light and the jar to decrease the light intensity. And we also use a photometer to measure the light intensity in our jar. And here's the result graph. The x-axis is the light intensity, and the y-axis is also the intensity of the sound. And it's very clear that they're positively related. So we can know that when the light intensity goes up, the sound intensity will also goes up too. And otherwise, they might decrease together. And our first experiment is that we want to test if the sound still can be heard when we use other kind of materials instead of soot. So in this case, we prepare 3 materials to test. First is our carbon powder and sodium bicarbonate, and later calcium hydroxide. And the result just very clear. All of them can produce a sound in 120 hertz since we connect it to our AC power supply. But there we found one thing very interesting is that the sound they produced was the maximum amplitude of the 120 hertz the sound was not the same, and it remains a misery. So we want to talk about it later in our discussion. And let's talk about the formation of the sound. As we know, in AC, the voltage will vary with the time, and in each period of AC, the light bulb will flash twice. And then we know that the voltage of the AC can be written in a periodic function. So we assume that the resistance of the light bulb is constant, so we can rewrite the power of the light bulb like this, applying the V function in it. We also know that the light and the power of the light bulb from the light bulb will be proportional to the consuming electricity power of the light bulb. So we can know that the power of the light can apply the function before and rewrite it like this. And the graph shows the power of the light with the time. And we assume that the light bulb was an ideal point light source, and its light field will be like its spheral shape. So we can know that the total power, the power absorbed by the light can be equals the radiation absorption rate of the suit times this area of the suit, and just apply the function we mentioned before and got a result. And so we can know that the total heat absorbed by the suit can be written like this: the integration of the upper function, and it also equals the capacity of the suit times the temperature difference. So from this, we can know that the temperature difference can be like the heat we got divided by the capacity of the suit. Then after some integration and calculation, we got this result. And it is also a periodic function. And from this case, in this, we can know that the frequency of this periodic function is twice the frequency of the AC frequency. 4 pi FAC times T, and this time is 4 pi FAC times T. So if we plot out the temperature difference and the time, we can know that the temperature of the suit will increase. And if we magnify this part, we can know that there's a fluctuation as the temperature increases. So it means that the temperature will suddenly increase very soon in a very short time and smoothen and increase very, very intensely. So that makes the sound. And we know that in thermal expansion, the volume difference will be proportional to the temperature difference. So it also means that the suit will vibrate in twice the AC frequency, and it also causes the sound wave of twice the AC frequency. Also, the suit may heat up the surrounding air, then later it chills down or stops to heat up. So that also causes the twice the AC frequency sound. And in physics, we call this photoacoustic effect. It's a recently developed technique using chemical analysis and medical study. It's because the periodical thermal emission makes the sound. And in photoacoustic effect, it's mainly talk about when the materials, or in this case, we talk about carbon particles in our experiment. The molecules inside, when they got illuminated, they reabsorb photons, and they might turn from the ground state to the excited state. And later, they may turn back to the ground state. And the periodical thermal emission will make the sound. And in this case, in photoacoustic effect, it follows the equation below. The absorption coefficient will equals to sound intensity divided by the light intensity and times the environmental factor. And so apply the equation this to our fourth experiment D. We can know that why does the maximum amplitude of the suit we use will be different. And we can know that the carbon is higher than calcium hydroxide, and higher than sodium bicarbonate. So here's a summary of our presentation. The soot was our sound source, and the jar and the cover does not affect the frequency. They are just acting like a resonant chamber. And the sound will be in the frequency of twice the AC frequency. And it will also reflect to the light intensity, and it will affect it by the material itself. The nature of the material will affect the sound intensity. And in physics, we call this photoacoustic effect. And that's all. Thank you.
Please, we will have 2 minutes for the opponent to ask reporter questions before we go to answer.
Okay, thanks for the reporter's report, and here will be some easy questions from me. So first of all, you mentioned that you use aluminum foil in your testing, and then you use carbon granules that they coat, right? Is that the difference?
Pardon?
At first, you used a aluminum foil inside the suit.
No?
Oh, so you use carbon granules at the holes,
Carbon powder.
carbon powder. Okay, the microphone, you put it inside or outside?
In observation, that's a mistake, but later we use just
Where did you put it?
attach
Is
to the-
inside the jar or outside the jar?
near to the cover.
Near to the carbon.
Just attached to the cover of the jar.
So it's outside the jar.
Yes?
Okay. Can you turn to page 12? In this graph, you can see that in the illuminated graph, the Fourier transform graph, you can see other peaks. Can you explain why?
That's also in the background, because of the background sound.
Okay.
But
then,
if you compare the...
we'll finish that in the discussion part. Can you turn to page 14?
Yes.
Okay. You mentioned that the jar will not affect the frequency, right?
Yes.
So the jar only acts like a resonance chamber.
It's acting like a resonant chamber. Right.
So you think that the size of the jar won't have
Somehow, if
there won't be any influences in the
Yes.
of the
you
jar
will-
volume.
If it is more concentrated, you can hear the sound.
So did you do any experiments changing the volume of the jar?
Yes, I did.
And I will take that into the discussion part further. And also page 31.
Okay, time's up.
Okay, thank you.
We'll have 3 minutes for opponents to
Can we move the chalkboard to the front? Thank you.
you will have to
Or maybe that's just maybe there. Then we'll.
Could you also move your open. 最好是就在那。
Sorry.
Next, we will have 14 minutes for discussion between the opponent and the reporter. The first 4 minutes, the opponent can take the floor.
Honorable juries, the opponent and the reviewer, good morning. I'm the opponent today from KSHS 44, and here are my questions. So first of all, I see that the reporter did some experiments on the intensity of the light and also all the other powders except carbon. But however, I have some ideas of other parameters, including the frequency of the light or the frequency of the flashlight. And also the problem statement states that to use an alternate current. And I would like to ask the reporter if he did any direct current in his experiment as a parameter. Also, I think that there are still some parameters the reporter left. For example, the size of the carbon coat suit, the size of the carbon, or the size of the hole, since he put the microphone outside the carbon. So the size of the hole might be an effect. And also the shape of the hole, because I would like to know if that might be taken into consideration as a kind of parameters. Also, and further on, also how the jar, the size of the jar, and also, and I guess that would be the parameters I would like to discuss about with the reporter. However, though he did some experiment to support his idea, I can't see a clear theoretical explanation behind this phenomenon, and I guess that would be also in my further discussions. And I guess that will be all. Thank you. So to the reporter, my first question will be. My first question would be, it's theoretically, how does the light transfer to heat when the light hits the carbon? Is it photoelectric effect, photoexcitation, photoionization, or other things?
The first one,
Photoelectric effect.
Photoacoustic effect. In basically, we'll call it photo.
I get your point. You're saying that the light will have sound, but I'm saying that I assume that you're talking about that the light, after it hits the carbon is heated. Are you saying that in your report?
Yes.
Okay, so how is the carbon heated? Because the carbon, after the carbon is heated, it will affect the expansion of the air to produce sound.
Yes.
So why will the carbon be heated?
That's one. Okay, I will explain the whole process of
It's a choice question. Do you have any
none of them
ideas?
above. It's photoacoustic effect.
Photoacoustic effect is that the sound can generate, the light can generate some sounds to be heard.
Now the suit will generate from sound to the light to sound.
So the light can generate, so the carbon absorbs the light and turns it into sound.
Yes.
So if there isn't any air inside the carbon, if we vacuum the carbon, it will still have sound?
No.
So
since there are no media, so the sound wave cannot be transferred.
So how does the sound start to oscillate?
To what?
Oscillate.
The sound?
Yeah, we know
so
that
the molecule in the air will start to. Okay, this page. When the molecule of it, when the suit got absorbed photons, it may turn from ground state to excited state.
Yes.
And later, they may go back to the ground state and have energy emission. In the book,
during the report of this part, it might be an effect of these three possibilities.
Photoelectric effect, it will
So which one do you think it is?
None of them. Because the first one, it will emit electrons. In this case, which did not.
And
There are four kinds of energy emission, and none of them.
So you deny the first choice, and what do you think about the second choice, a photoexcitation?
You mean the electrons inside the molecule will turn from ground state to excited state?
Yeah.
Do you mean? Yes, it was mentioned.
So you think it's photoexcitation?
Yes.
Do you know the difference between photoexcitation and photoionization?
Ionization might lose some electrons, right?
Might lost some electrons. Can you be more specific?
Like sodium become the ion of sodium. Do you mean that?
The ion of sodium. Yes, but it's triggered by a photon.
I can't catch your point, sorry.
Okay, so you think it's photoexcitation that causes the heat?
Yes, but the process of making the heat is after the excitation, since the electron
I'll
turn
make
back.
a summary of your theory, and you can tell me what my problem of your my understanding is. Okay?
Okay.
Okay. So the light first hits the carbon powder, and then the carbon powder, due to photoexcitation, the electron jumps to an excited state and then bounces back to its ground state. And during the process, the electrons produces energy, causing the air to have expansions. And due to the expansion, there will be sound. Is this what you mean?
Yes.
So you think the effect will be so quick that the air of expansion is so quick to produce the frequency that it can be heard?
Yes.
Okay, so then we'll move on to my next question. I see that you answered the carbon one. And what kind of microphone did you use? Sorry. So we'll move on to my third parameter. Different colors of light. Do you have any experiments?
Since we apply different frequency of the light, we only use incandescent light bulb. If we can, I would like to use.
Can you be
AC
more
light, but-
specific?
Okay, I did not do that, but I assume
You
that
did
it
not?
will affect.
How?
Since I mentioned the molecule of solar photons, the frequency of the photon must be higher than a certain level. But in our experiment,
Will be higher than a certain level.
so that
So you think the color of the light photons must have a higher frequency than the frequency to excite the state, right?
yes.
You made a mistake here.
Okay, listen.
Well, we're talking about photoexcitation. The frequency must be the same.
You have higher frequency, they will get more energy, and
Maybe we'll move on to my next
the
parameter.
excited state will be higher.
Have you controlled the flash frequency of the light?
Yes, in our second experiment.
And can I see more of, again, the results?
Okay, could you please turn to the apparatus of this one? Yes, we use inverter to provide different frequency of the AC part. Since we know the light bulb will flash in twice the AC frequency, so the flashing frequency is controlled in this experiment.
And so you believe that the flashing frequency will be the flashing, the 2 times of the flashing frequency will be the same as the frequency you heard.
Yes, we use high-speed camera to check that in our experiment.
Let's think about the problem since you placed the microphone outside the jar. This is the jar, and this might be the hole, okay? And this is the hole.
Yes, I
And
understand.
due to the expansion, there will be an airflow from the hole. And airflow will be floated outside.
Sorry, which part is inside of the jar? Okay, I get
Okay,
the point.
so there will be an airflow here, right? I want to confirm the question.
Yes.
Yes, and you place the microphone here.
Now, attach it here.
You attach it to there. Okay, but there's still a question here. Do you know that while we're talking about fluid mechanics, we use the continuity equation to describe the conservation of mass.
Pardon?
We use the equation of continuity to describe the conservation of mass in fluid mechanics. Can you get my idea? So the bigger the hole will be, the velocity here will be smaller.
So the amplitude of the sound will be reduced.
I'm stating my problem. So here is the smaller hole, and here will be a smaller hole, and the velocity will be bigger. Can you get my point?
But when the hole is too small,
It's a yes or no question.
yes.
It's a yes question, right? Did you do any experiments changing the size of the hole?
No, in
No.
this case, we focus on the frequency of the sound.
But do you think it will affect since the velocity changes?
Yes, it might affect the amplitude of the sound.
It might affect the amplitude.
Yeah, or the sound intensity.
The
Since we
sound-
know
Why the sound intensity? Because I thought that V will be, there isn't sound intensity in this formula.
when you have higher velocity of the airflow, if you have a fan beside you and you
I
hear
just
the
just
sound,
answer my question. So what V will be the multiplication of frequency and the lambda. And you mentioned that the bigger the velocity is, it will affect the amplitude.
you are
How?
saying the airflow, but not the sound wave. You
Yeah.
mentioned the wrong thing
But
here.
well, you mentioned that the sound wave is transferred by air, right?
Yes, it's transferred.
And then
it's
the air
vibrating.
has the velocity. So
No,
which
it's vibrating, not the airflow.
So-
So it's the problem is
so you think the frequency will not change,
the frequency will not change.
and what will change?
The amplitude of the sound will
Okay,
change,
the
will be
amplitude.
affected by the jar and
Maybe
or
we'll
by the
just
cover.
move on to my next question.
Thank you.
Did you try DC?
Yes, and the sound will not be produced since the light is continuously lightened.
Okay, and how about the size of the carbon coat?
Okay, it will affect the contact surface area of the suit. And we
Do you
did.
have any experiment results to show us the size of the carbon
You
coat?
say the surface area.
Yeah.
Yes, the dash to.
Let's be quick.
Wait. In this case, we use different. The x-axis is cm square, and the y-axis is the
What's the x-axis?
centimeter square of our suit,
Uh-huh.
the area. And when the area goes
Why
up,
didn't you use percentage
percentage of what?
of the jar?
Of the jar, since it is not clear, if we use different kinds.
Okay, so let me make a small summarization. You believe that by putting carbon powder onto a plate and shining light, flashing light onto it, a sound can be heard. Can be heard.
Yes.
Can be heard. Are you sure it can be heard?
Using AC,
I'm saying AC.
and we coat one side of.
I'm not saying coating. You said that a jar doesn't really affect, so if it's
Yeah.
not, we just place a plate and then place the carbon
Yes.
powders onto it.
Yes,
A
we
sound
did
can
also
be heard.
further investigation in our first experiment I mentioned in the slide.
How strong should the intensity of light be?
There will be smaller than the one we put in the jar, since the sound was not that concentrated. Sorry, the sound was not that concentrated.
So about how small is the sound?
How small is the sound? We compare them. Is in this case, it's 40,
That's 40.
40
Wow.
some 40 somehow decibel.
40 dB. 40 dB is really high.
Yeah, but this case we emphasize sound that all of them were amplified and in the same method. So we only make a comparison.
I get your point. Let's move on to the next question. You mentioned in the question part that you changed the size of the jar.
Yes, we have used these bottles, jars, or even metal plate here, and we try to measure. It will not affect the frequency, so we did not put the graph here. It only affect the amplitude.
But do you think the shape of the jar will change? What will the shape of the jar affect?
If it affects somehow the intensity of the sound, and it is if the sound was done in the
Like how? In what way?
It depends on
It
what
depends.
kind of the.
So what's the difference between this and this?
Since this is smaller.
Okay.
This
I-
one?
I
Okay,
will
thank
start.
you.
Next will be 1 minute.
Thanks for the fruitful discussion. We have some discussions mainly on the basic theoretical concepts of how the heat is transferred into the expansion of the air and then producing it into sound waves. However, reporter made a crucial mistake on here. He's right on photon excitation, but it's not that the bigger the frequency is, the bigger the excitation is, because there is a specific frequency for you to excite the electrons. And also, so we move on to more parameters, and we found that like different colors of light and different flash frequencies. And also moving on, we talked about the difference between alternative current and the direct current, and also the size of the carbon powder suit. And then the size of the hole. As he mentioned, we reached a consensus that the bigger the hole will be. Thank you.
I guess that will be all. Thank you.
First of all, I've got some questions for the reporter. Sorry, opponent, can you return? Okay. And first of all, I have some questions to the reporter. So, have you done the experiment without putting carbon powder inside the jar?
Yes, it's all in the background sound, and that's the sound we record from the empty jar.
So did you eliminate the other light source like the fluorescent light? Because in your observation, you didn't. You did it in the...
Yeah, we try to use that, but not in the slide. We have mentioned it, we have done that experiment before. It will not affect the frequency.
So you mean that you do this experiment under light? There are other light sources.
Oh, you say that in our experiment we turn the light on and you
No,
okay.
Did you turn off the light?
No, we didn't.
Okay.
We did it in a dark room.
So what do you, did you make sure when you're changing the different powder, you make sure the thickness of it is the same?
The thickness and the surface area are all controlled.
So can you turn to page 17?
17, please. Yeah. 17. Here.
So can you, because the unit on the y-axis, I think is kind of strange. Sound pressure level y.
It is not measured for a decibel meter. It is somehow a comparison, so the decibel can be used in comparison level. So in this case, it is not actual decibel we use.
Why there are hertz in the units?
It's a spectrogram, and somehow we call it FFT, analyze the frequency and the intensity in certain frequency.
Okay, well, so, because I think your light bulb is really very strong. It will also provide the heat.
Yes.
That is made by the light bulb. So did you consider the heat, not only the light?
Yes.
So how?
In every experiment, we used the glass to cover on the top of the concentrate.
Okay.
Okay.
Can you turn the page with the B ABS?
Which one?
Okay, well, I jumped to that. So to the opponent, what do you think? Because you asked the reporter the color of light, and can you answer your question?
Yeah, the color of light will be determined by the frequency of the light, and so to excite the photons to there you have this your frequency there should be a number. There should be a frequency range.
When you're talking about can you look at the question 3? Because you mentioned V equals to F times lambda, but you mean that V is the sound of the velocity of the air. Do you mean by that?
3 minutes? 2 minutes?
a viewer from the team Fire Drill Walls. So let's take a quick review of this problem statement. They said that a jar with a layer of soot inside a jar, and when the AC light bulb, the light hits the jar, it will produce a distinct sound that can be heard. And the problem statement wanted us to investigate this and explain this phenomenon. Well, here comes to the reporter's main point. In their presentation, they mentioned that when the light is on, the AC light is on, the small humming sound can be heard. And the frequency of the sound is actually 120 hertz. And also, they said that the jar acts like a resonant chamber, and the frequency of the sound will equals to 2 times the frequency of the AC power supply, which is 60 hertz. And when the light intensity gets higher, the sound intensity will also increase. And they also tried on the different material. And on their discussion part, they said that because the soot heated up the air, which makes a pressure wave, which is called the photoacoustic effect. And here the reporters make advantage. Well, I think they showed a very clear video on their observation, and I think their equipment of their experiment is really well. And however, there's some suggestions. Well, I think they can focus more time on and explain their theory more clearly, and as the same as the opponent, I think they can work on more parameters like the color of light, the size of the jar. And here the opponent's main point, where they talk about other parameters like the volume of the jar and the different light color, and also they asked the reporter how the light turns into heat, and the reporter answered that it is called a photo. Well, they also asked about the difference between the AC and DC power supply. And they talk about the size of the hole, the size of the jar, and the size of the carbon, how it really influence the result. Well, there are I think the opponent had really a great discussion about many other parameters that I have just mentioned. And they think that the reporter made a mistake on the color of lights because they think that it will be a frequency that will make a bigger sound. And there are some suggestions to a opponent because I think they made some mistake in V equals to F times lambda because I think their V will be, they mentioned in their question the V is the velocity of the airstream, but in this formula, the V must be the velocity of the sound wave. So I think it's a little bit different. And also, they can focus more on their experiment and their experimental data and the result. And that's all for my taking floor. Thanks for listening.
Thank you for the opponents and reviewers' suggestions. And I think I misunderstood one thing. I mentioned the frequency of the light was the flashing frequency. I misunderstood the opponent's question, and I made a mistake. I'm saying that when the frequency of the flashing frequency goes up, the sound in frequency will also goes up. But how about the frequency of the photon? When the photons was the frequency of the photon under a certain limit, for example, we use infra, the sound might not be produced since it cannot excite the photon and the electron from the ground state to the excited state. And we also talk about the microphone, the jar size and the hole size. I think we talk about this part, and the hole size will only affect its amplitude. And about the theory part, it was also in the calculation, and the result got was that there is a fluctuation as the temperature increases. So that makes the sound that makes the sound, since the temperature suddenly increase, making a pressure wave. So that's why we can form the pressure wave. And about the experiment, the flashing frequency we controlled in our second experiment, since we use inverter to control the flashing frequency. And about the shape of the jar, it is some further investigation. It only amplify the sound, or if the sound was not in the nature resonant frequency of the jar, it might affect the frequency of the sound we heard. That's all my concluding remark. Thank you.
We will have 5 minutes for the jury to ask questions. Anyone? Professor Tan?
I think we have microphone. I have a very nice question for the reporter. I think in the problem, it is stated that the question is coat 1/2 of the inside of a jar with a layer of soot and feel a hole in its cover.
Yes.
It mentioned a very specific setup, 1/2 and the inside.
Yes.
So do you have any comment on this kind of setup? Do you need this kind of setup to produce a sound? For example, if you just coat the whole inside of a jar.
Okay. I know.
A sound?
Yes. I think the problem wants us to do that because we have half of them, keep them transparent so that light can get through the jar and get through the soot inside. So that makes a sound. If we coat over that, the light might not go to the inside, and that's pretty much harder for the sound to be produced.
Just follow up. So it doesn't matter it's inside, outside. Actually, in your experiment, even if you do it outside without a jar, you
Yes.
can still hear the sound.
Yes.
Any? Professor Chen?
In your experimental result, when you see the intensity spectrum, except the peak, you always see some kind of background shape. This is probably sort of that following this is over.
This one?
Except the peak, you also see a background shape.
Yes.
Can you tell us what kind of information we can get from that, maybe reporters, women, and the reviewers?
I think some of the background in our environment there is some background noise, and that's a noise thing. We can make sure that there are noise since we record background sound and compare
Some kind of
shape. Oh, this part we have observed this part very clearly. We know that in every microphone we test, if we recorded the first time. Sorry, I will draw this. This is the time and this is the amplitude. And we observe that when we record, the intensity of the sound will be jump to very high and later back to the normal situation. So I think that might be some problem with the microphone since we use every kind of microphone and that's a problem.
According to this graph,
maybe experiment is some kind of background.
yeah, and I guess that might be some noises or other some noises from some noises or hisses from the space, the area. Because every peak, if there is a peak in the Fourier graph, it means that the frequency is dominating the wave.
Okay, and I think just the noise in our environment, so it will make this kind of graph. And also, and some of his graph I saw, its frequency is about 2 times 120 hertz. It means that because they said that jar acts like a resonance chamber. So I think there might be some overtone of it. That means 2 times 120 hertz. All right, more.
So just if it's pretty the noise, I don't think you will see some specific shape. It's just the time.
Don't have to worry about that. One more quick question. Professor Tom, again.
Professor Cao,
Yeah, you should.
You mentioned that the sound is caused first by photo excitation. So have you tried to figure out the cutoff frequency if it is really photo excitation?
I think the origin of photoacoustic effect is because of photo excitation, and that's why I say that's why I agree with the opponent.
Yeah, but my question is that have you tried to work out the cutoff frequency?
Sorry, I didn't do that.
Okay. Well, I guess we can allow quick questions.
That's a good question. Did you ever try to record empty jar with the light on?
Record the empty job. Oh, they're all in background sound. They're all in background sound. We have some background sound, and that's with the empty job.
Background sound is it's not clear to us. Is the background sound without the light on, or is background sound without the suit?
Allow the light on.
Is the light on?
Yes.
Without the suit inside.
Yes.
You know, first time feel materials. You will have tried some material that do not give this effect.
Sorry, I didn't.
Okay, that's it. Okay, thank you. What's the purity? We will start with your radio piece. Turn the numbers toward this side. Okay, on this side. First of all, a reporter, please. You don't have any hiding. Okay, everyone's ready. Starting from left. 9, 7, 9, 9, 9, 8, 9, 9, 9, 7, 8. Okay, we will have a break, so no, we don't continue. Oh, sorry. I shouldn't be here because I never took part in this. Ready? Okay, for the opponent team, 7, 7, 7, 8, 8, 8, 7, 8, 8, 8, 9.
Thank you.
If you are ready, please, great. Okay. 8, 8, 8, 9, 9, 8, 8, 8, 8, 7, 7. Okay, now we will take 10 minutes break. That's the part I like most.
不好试，我这边要试。
那边是低档的就 OK 了。